Hey, welcome to the Explainer. Every time you check your phone or see that reddish-brown rust on an old fence, you're actually witnessing the exact same force at play, just pointed in different directions. It's this incredible, unseen battle of chemistry. On one side, it's a controlled reaction that powers our world. On the other, it's an uncontrolled one that causes it to decay. Today, we're diving deep into that hidden world. First, we'll see how we harness it inside our batteries, and then how we fight back when it turns into corrosion.
So, here's our game plan. We're going to start by unpacking what a battery really is. Then we'll get into the modern powerhouses, the lithium-ion tech that's everywhere. After that, we do a complete 180 and look at the flip side, the science of decay, aka corrosion. We'll see how it happens, and then we'll wrap up with the super clever ways we're winning that war. All right, let's get into it.
First things first, let's pull back the curtain and really get to the heart of this thing. What even is a battery, and how does it store energy?
Okay, so what is a battery? Well, the first thing to know is that it's not really a single thing. It's more like a team. It's a collection of two or more of what we call electrochemical cells, all working in concert. And each one of these little power factories has two key parts, two electrodes, and this special stuff called an electrolyte sitting between them. That electrolyte lets charged particles, or ions, travel from one side to the other. And that controlled movement, well, that's the whole magic trick. That's what stores and then delivers the electricity we use every single day. Now, as you probably know, not all batteries are the same. They generally fall into three big categories. You've got your primary batteries. These are your one-and-done, use-and-toss types. The chemical reaction inside only goes in one direction. Then you have the secondary batteries. These are the rock stars of the modern world. Think about your phone or laptop. Their chemical reaction is reversible. You can charge them, drain them, and charge them again hundreds of times. And then there's this really cool third type, reserve batteries. These things are designed to last for decades on a shelf, sometimes over 20 years. They keep their insides separated and inactive until, bam, the moment they're needed. Perfect for emergency gear.
So, that brings up a really important question. Scientists can cook up all kinds of wild battery chemistries in a lab, right? But what does it actually take for one of those ideas to make the massive leap from a lab bench into your laptop or your car?
Well, it turns out the checklist is pretty brutal. Obviously, it has to have enough power, the right capacity and voltage, but it also has to be the right size and weight. It's got to be tough enough to handle being dropped or getting hot and cold. And safety? Oh man, that is absolutely non-negotiable. On top of all that, it's got to be cheap enough to make, last a long time, not be a total disaster for the environment, and pass a whole bunch of regulations. It's a real balancing act, and it's why new battery breakthroughs take so long to hit the market.
Okay, so with that tough checklist in mind, let's take a closer look at a couple of technologies that actually made the cut and are changing our world. The famous lithium-ion battery and its very different cousin, the fuel cell.
So the magic of a lithium-ion battery is this really elegant, beautiful dance that's happening on a microscopic level. When you're using your phone, when it's discharging, tiny lithium ions are literally swimming from one side, the anode, over to the other side, the cathode. As they make that trip, they release electrons, and that's the electricity that powers your screen. Then, when you plug it in, you're running the movie in reverse. You're using power from the wall to force those ions to swim back to where they started, ready to go all over again. It's this perfect, reversible cycle.
And that elegant dance is exactly why Li-ion is king for electric vehicles. It's got high energy density. That means it can pack a ton of energy into a pretty small space, which gives you your range. It's also got high power density, which means it can release that energy super fast. That's what gives you that crazy acceleration. Throw in a long lifespan and the fact that they're relatively lightweight, and you've got the secret sauce for the entire EV revolution.
But then you have fuel cells. They also make electricity from chemistry, but they are a totally different beast. The best way to think about it is this. A battery is like a sealed container. It stores all its energy inside. A fuel cell, on the other hand, is an energy converter. It doesn't store anything. It takes a fuel from the outside, like hydrogen, and converts it into electricity on the fly. So while a battery eventually goes dead and needs to be recharged, a fuel cell will just keep running as long as you keep feeding it fuel.
Okay, so we've seen how we cleverly control electrochemistry to get what we want. But now we're going to flip the coin and look at what happens when that exact same process just runs wild and out of control. It's time to talk about the science of decay, aka the world of corrosion.
So, here's the big idea. Corrosion is basically just an unwanted battery. Seriously, it's the natural tendency of a refined metal, like pure iron, to try and get back to its original, more stable state, like the iron ore it came from. When you see iron rusting or silver tarnishing, what you're seeing is that metal reacting with its environment, with oxygen, water, you name it, and slowly falling apart in the process.
And this decay pretty much happens in two main ways. First, there's chemical, or dry corrosion. That's a direct chemical attack, usually from a gas just reacting with the metal's surface. But the far more common and usually more destructive type is electrochemical, or wet, corrosion. And this is the one that's a tiny battery. It needs a liquid, an electrolyte, and it sets up these little positive and negative zones all over the metal, creating a current that literally eats the metal away from the inside out.
Okay, so let's dig into that wet corrosion a little deeper, because this is how we see things fall apart in the real world. We're going to look at some of the most common ways this unwanted battery action affects everything around us. So here's a classic real-world puzzle for you. Maybe you've seen this in an old house. You've got a shiny copper pipe, and there's a steel bolt attached to it. The steel bolt is rusted and crumbling to bits, but the copper pipe, right next to it, looks perfectly fine. What is going on there? Well, the answer to that puzzle is the first one on our list, galvanic corrosion. When you stick two different metals together with a little bit of moisture, you've just built a battery. The more active metal, in this case steel, becomes the anode and basically sacrifices itself. It corrodes like crazy to protect the less active metal, the copper. Then you've got pitting corrosion, which is nasty. It's a very focused attack that creates these tiny, deep holes, or pits. And then there's waterline corrosion, which is just fascinating. On a ship, the part of the hull just under the water gets less oxygen, so it becomes the anode and starts to corrode. The part right at the waterline gets tons of oxygen, so it becomes the cathode and stays protected. A difference in oxygen is all it takes to create a battery.
So what makes all this happen faster or slower? Well, a few key things. The purity of the metal matters a lot. Impurities can create tons of tiny little corrosion cells. And of course, the environment is huge. Hotter temperatures speed things up. More acidic conditions, a lower pH, are really bad. And more humidity, well, that provides the liquid electrolyte that this whole destructive process needs to get going.
Now, I know this all sounds pretty bad, like an unstoppable force of nature, but here's the cool part. We've figured out some incredibly clever ways to fight back. So for our last section, let's look at how we're actually winning the war on corrosion every day.
The main strategy we use is called cathodic protection, and the idea behind it is just brilliantly simple. We know that corrosion, the actual eating away of the metal, only happens at the anode of our little unwanted battery. So the whole game is this. If you can somehow force the thing you're trying to save, like a pipeline or a bridge, to be the cathode, it just can't corrode. Game over.
And we mainly do this in two ways. The first is the sacrificial anode method. This is basically turning that galvanic corrosion we saw earlier into a weapon for good. We'll literally bolt a big chunk of a more active metal like zinc onto a ship's hull. That chunk of zinc willingly becomes the anode and corrodes away, sacrificing itself to protect the steel hull. The other method is called impressed current. This is for the really big jobs. We actually hook up a power supply and pump a small electric current into the structure, basically overriding the natural corrosion and forcing our pipeline or tank to be the cathode, stopping decay cold. So we end up right back where we started, looking at the two faces of electrochemistry. One side gives us the clean power for an electric future, and the other side is this constant nagging force trying to tear that future down. It's the controlled dance of ions in a battery versus the uncontrolled chaos of corrosion. And that leaves us with one final thought. As our world gets more and more electric, what's going to be the next big breakthrough in this never-ending battle we're fighting both for and against chemistry? Thanks for joining us.